Good morning, everyone. I'm Parminder Bhatia, Head of Machine Learning and Research at AWS Health AI. A bit of background about myself. I was one of the founding members and lead scientists for Amazon Comprehend Medical, which is our healthcare-specific NLP service. In the last 2 years, we've also launched Transcribe Medical, which is our ASR service tailored towards healthcare, as well as recently launched Amazon Health Lake, which is our analytics platform to accelerate machine learning research. Here's the outline of our talk, where we'll start with the accelerated growth of COVID-19 publications and its corresponding datasets that have been created. Then we'll talk about AWS CORD-19 search, which is our search to curate and understand these publications, as well as talk about some of the performance evaluations of our search engine. Then we'll talk about COVID knowledge graph as to how we constructed that, as well as its potential applications. With the global outbreak of coronavirus, there's been a lot of focus on research on coronavirus with thousands of research articles that are generated every day. CORD-19 dataset is a collection of millions of those research articles, which was created with an aim to connect machine learning community with biomedical research experts and policymakers to identify effective treatments and management policies for COVID-19. Our goal with AWS CORD-19 was to provide a scalable solution to biomedical researchers to be able to access COVID-19 information easily using advanced NLP techniques. AWS CORD-19 provides easy-to-use search interface where users can query in the form of natural language questions as well as keyword search. Here's an example of a query that a user can make. For example, a user can ask, what is the mean value of RO for COVID-19? Here we can see that the search engine is able to identify the answer and highlight that, which is like 3.28. It is able to identify the corresponding document associated with that as well. As shown in this example, the major capabilities of Amazon CORD-19 are document ranking based on relevance, as well as question answering and passage ranking, which extract and highlight the relevant answers based on the different information. AWS CORD-19 provides easy-to-use search interface where users can query using natural language questions in addition to traditional keyword-based questions. In order to retrieve these answers, we want our search engine to be biomedically clinically relevant, which has a stronger understanding of biomedical understanding to be able to understand these questions. Here's a quick example of ACS question where a user can ask question like, what is the mean value of RO for COVID-19? Here we can see that the search engine is able to identify the answer from a given document, which is 3.28, as well as its corresponding passage where the document and the answer was found. If we look into ACS, and in this example, ACS provides capabilities such as document ranking based on relevancy, passage ranking, and question answering, where it is able to extract and highlight the answer directly from the top relevant passages. In addition to that, it also has capabilities such as topic filtering, as well as paper recommendations, which we'll talk later in our talk. Here is the high-level overview architecture of ACS, where the first process is powered by data enrichment, where the data enrichment process is done using the output from Comprehend Medical, which is our healthcare-specific NLP service, as well as topic modeling, where the outputs from both of them are fed to create COVID-19 knowledge graph. The idea behind creating this data enrichment process is to make our search engine clinically more relevant. Once the data has been enriched, it is then indexed into Amazon Kendra, which is the core to our natural language-based search. One of the advantages of this system that we had built using the technologies that we talk about here is that these systems are quite robust to zero-shot or few-shot settings, which makes it ideal for COVID-19 research, where every day thousands of clinical trials are running, where new information about medications and medical conditions are coming out every day. Next, we'll deep dive into individual components. We'll start with Amazon Kendra, which is our enterprise-level search engine. The first component is around document ranking, where the idea is how the system can retrieve ranked list of documents based on natural language questions as well as keyword-based questions. For example, a user can ask question like COVID-19 incubation period, or they can also ask in the form of natural language question like, what is the incubation period of coronavirus? In addition, it also has capabilities for passage ranking and question answering, where it retrieves the top passages and extracts the answers from that. The next step that we're going to talk about is data enrichment process, where the data enrichment is primarily done by Amazon Comprehend Medical to create knowledge graph as well as to support our search engine. First, let's talk about Comprehend Medical. Comprehend Medical is our healthcare-specific NLP service, which is used to extract entities, which is Vyvanse, for example, over here, tie these different entities in the form of relations. For example, Vyvanse over here would be tied to 50 milligrams in the form of relations, which is dosage, as well as do entity linking. Entity linking is a task of assigning a unique concept from a knowledge base to entities mentioned in a clinical text. There are various challenges associated with entity linking in medical domain. Firstly, entities are quite ambiguous. In addition, medical notes contain a lot of typos, structure, lack of structure, and abbreviations, which makes it difficult to build a robust entity linking system that can work well across these different specializations and domains. Here's an example where we can see that tenderness over here is referred to an ICD-10 concept, which is pain in the left finger. And if we read the entire document, we can realize that in order to tie tenderness to the right concept, we have to heavily rely on the contextual information that is provided in the document. Also for CORD-19, another challenge is that a lot of drugs are novel zero-shot learning problem, since the system would have never seen these type of drugs. In addition, Comprehend Medical also has a temporality feature where the idea is how can we create the timeline for a given document or for a given patient. This feature was extremely useful to be able to understand biomedical research articles that were pertaining to patients, where we could actually create the timeline for a patient as to what medications were taken across the timeline, as well as how the conditions progress with time as well. In addition, we also added additional capability for biomedical topics to filter the search result. Here, the idea is that for a given search query, the answer that the user might be looking for might vary depending upon the area of interest for a user. For example, for a question like, what is the origin of COVID-19? The answer for that might vary whether a person is looking at it from the clinical trials perspective or if the person is looking from the genomics perspective. Since we did not have any label data, we use ZLDA, which utilizes priors that allow the model to enforce certain topics that the users have manually created or that the user wishes to be clustered together. For actually providing this prior information, we use the help of biomedical research professionals, and the information was actually then fed into the model. After building ACS, the next component was how do we evaluate its performance? To be able to evaluate its performance, the best way was to actually compare it with similar search engines who offer similar capabilities of question answering and document ranking. Here we looked into two different search engines. The first one is COVIDx, that is powered by T5 technology to be able to do question answering as well as passage ranking. And the second one is Google's Research Explorer that is powered by BERT, and that uses similar functionalities and provides capabilities such as semantic web search that support both natural language questions as well as keyword-based questions. To be able to evaluate all the systems, we actually compared ACS with COVID-19 RE as well as with COVIDx for document ranking, passage ranking, question answering components respectively. Now we move on to the different data sets that we use for evaluation. The first data set that we used was TREC COVID-19, which was used for document ranking evaluation, which primarily consisted of 40 different topics that were actually curated based on the top questions that were asked on National Library of Medicine. Together with these questions and CORD-19 corpus, participants were asked to provide a ranked list of documents based on different topics. Once this data was aggregated across these different participants, we actually looked into the depth pool of 10 to 20, where what that means is for each topic, top 10 to 20 documents were selected across these different participants, which was aggregated together. Next, biomedical researchers or experts were asked to assess these documents, and where they were given a query as well as a document, and they had to identify whether the document was good, fair, or bad. For question answering evaluation, we actually used COVID QA dataset that consisted of 27 queries collected as the most promising research direction questions. Since the annotations for these were not provided on the complete dataset, we actually used internal annotations to make passage ranking and question answering annotations. For each query, first we collected top 50 results from each of the search engines, which was characterized by article, link, display, passage, as well as highlighted answer. After that, we hide the search engine and the rank information and randomly shuffle the results, where the annotators were provided with a query, document, passage rank, and they were tasked to identify whether the passage was relevant, as well as if the answer was highlighted was right or not. The questions, the results were actually shuffled, and the search engine information was actually hidden in order to remove the location as well as the engine bias that can be incorporated. Here's an overview of the evaluation datasets, where we looked into track COVID-19 for document ranking evaluations, and we used COVID QA for passage ranking and question answering. Next, we move on to the evaluations. We first start with document ranking. Here is an example of one track COVID example, where each topic consists of both keyword-based query as well as natural language questions. So for keyword query over here, we have coronavirus, and the natural language question associated with that is, what is the origin of COVID-19? We evaluated all the three systems across different evaluation metrics like precision at K, recall at K, as well as NDCG. As we can see from the results here, that ACS consistently outperforms all the other systems on both keyword-based query as well as natural language-based query. Next, we wanted to evaluate how these systems are robust to different query variations as we move from keyword-based query to natural language-based queries. So in order to evaluate the robustness of the result against the query variation, we actually compared two different metrics. One was the exact match of results coming out from keyword query to natural language query, and the second one was F1 score, where for both of these metrics, higher score is better. And again, we can see that ACS consistently outperforms both the other systems, thereby highlighting the fact that ACS is actually more robust against query variations. Next, we evaluate COVID QA 27 queries for passage ranking and question answering, where the evaluation was done with precision at K. And again, we can see that ACS for both passage ranking as well as question answering consistently outperforms both the other systems. I would like to highlight over here that similar evaluation was done by an independent research, which found similar trend on document ranking and passage ranking, where Amazon CORD-19 consistently outperformed these other semantically relevant search engines. Next, we move on to COVID-19 knowledge graph. One of the core components of ACS COVID-19 is actually the knowledge graph that was constructed. We use knowledge graph for a variety of different applications. The first application was around paper recommendation, where the idea is that once the user selects or clicks on a paper, we provide them with the relevant papers associated for a given paper so that the user does not have to go back and search again. The second functionality is actually around drug discovery or repurposing that we'll talk later in our conversation. Talking about COVID-19 knowledge graph. Knowledge graphs are structural representation of relations between real-world entities where it contains a head entity, a tail entity, as well as a relationship type connecting them. In our scenario over here, each paper is connected to different papers in different kind of relations related to entities, authors, citations, etc. The resulting knowledge graph continues to grow as CORD-19 dataset continuously increases. And currently, when we looked into the snapshot, it contained more than 500K different entities with more than 5 million different relations. Once the knowledge graph was constructed, the next phase was around creating knowledge graph-based embeddings. Knowledge graph embedding models generate embeddings solely taking into account the structure of the knowledge graph. However, in order to make a robust system, we want an ideal system to incorporate the structure of the graph as well as to look into the semantic representations where similar papers should also be kind of grouped together or linked together. So for knowledge graph, we generated embeddings from DGL library, which is our open source library that is provided in the link below, as well as for semantic embedding, we parse the abstracts through Cybert. Next, we show how these different embeddings perform regarding the paper similarity calculation. Since we did not have any supervised signal when we were actually working on this problem, we actually looked into topic similarity between the source and the recommended papers to evaluate the embeddings. Here we looked into the top paper and its top 5 recommended articles for each of those different embedding methods. And then we looked into the topic distance where less distance is better. And here we can see that the best performing system or the embedding is actually a combination of semantic engine as well as knowledge graph embedding, which has the least score, thereby having the most topic similarity between the document and its associated recommendations. Next use case we covered is around drug repurposing for knowledge graph, where the idea is how can we improve the efficiency and speed of discovering new treatments. One of the challenges associated with drug discovery is that it is a lengthy and a costly process. And how can we redevelop or reuse existing drugs for use in novel diseases? The major component of knowledge graph was of drug repurposing knowledge graph construction was actually constructing the knowledge graph. The first component which we used was similar to what we had shown for COVID-19 knowledge graph, where the data was passed through the component medical as well as other data enrichment process. In addition to that, we actually aggregated a lot of publicly available data sets and did similar analysis and then created a corresponding graphs with different kinds of relations related to genes, compounds, as well as drugs associated with them. Once the graph was constructed, we then used different knowledge graph embedding methods such as TransC as well as distance model, which utilize different distance metrics. And all of this was constructed using our DGL knowledge graph library that has been optimized for actually learning and generating these knowledge graph embedding models. Next, we wanted to evaluate how our knowledge graph or how good our knowledge graph was. So we considered the task of identifying links between drugs and treatment as a link prediction problem, where we evaluate new links between drugs and diseases using a treatment relation. For a given disease, which is CORD-19, we actually selected top 100 drugs from the system. And to be able to evaluate that, we wanted to see how it corresponds to the actual drugs that are used for drug repurposing in practice. We found that 6 out of the top 100 predictions were actually part of the 32 validation drugs that were being used for clinical trials. Next, we did similar analysis, but over here we consider the link prediction problem between drug and genes, which is causing the virus, and we looked into the relationship type of inhibition. And again, we found when we did analysis and ranked the top 100 drugs, we found about 17 of those drugs were actually used in clinical trials for drug repurposing. Here are some certain future directions that we would want to incorporate as part of drug repurposing knowledge graph, where firstly, we can actually enhance this knowledge graph by combining the outcomes from medical trials or even combining it with medical EHRs or patient EHRs associated with them. We can actually combine this with gene sequencing data for different genes and chemical sequences, thereby combining the clinical and the gene sequencing data together. Another interesting research direction is actually how we can incorporate domain expertise while we're training these embeddings as well. Here is the summary of our talk, where we first looked into AWS CORD-19 search engine that supports document ranking, passage ranking, as well as question answering. We evaluated our system across different benchmarks and compared it with other semantic search engines on document ranking, passage ranking, as well as on question answering. Next, we also looked into how the knowledge graphs were constructed, as well as into its potential applications. Thanks everyone for your attention. I'm happy to answer any questions. Thank you.